Weibo works really well when you've already got a process and it's small changes. If you're doing like a big change, like if your bars have like major defects in them and you're trying to do like a Weibo analysis, the flaw range is so big it's hard because I think you've got different types of flaws. You got delamination versus like the pores inside. This is good for fixing one type of flaw at a time. So I don't know where everyone is, but it's 9:40 and we got not a ton of time. So on Friday we're going to do some examples. We'll try and make some Prince Rupert droplets. I have to find the blowtorch. I don't know where it went. But we do have a few things today, and I wanted to wrap up with a little bit on Weibull. So how do you do Weibull? I just picked some random data. I told Excel to give me a random number between 300 and 600 here. We've got 30 data sets. So this might represent the values you get for strength or time until failure or whatever else for 30 samples. So what's the first step? What do we do? Rank them, right? So we need to copy these. And I'm going to need to paste them as values. So you have paste special and we're going to hit values. Because right now they're formulas. That's going to mess it up. So now I've got these as values. What the? Oh, it must recalculate. Oh, yeah. When you post something, it redid these. So that's fine. So now we don't need this column anymore, right? We've got our values over here. I guess we can leave it, but we can just ignore it, right? So here's these. What's our next step? We said rank them.
So you want to sort them first from highest to lowest.
That's ranking. So to do that, you go to home, then sort. We're going to do smallest to largest, and we've got them all ranked, right? So now what do we do?
So this is the fracture stress.
This could be fracture stress. It could be time until failure. It could be elongation. It could be whatever your criteria is that you're doing with Weibull. It works well with things that follow brittle fractures. So failure is a really good one, but I've seen it done for time and elongation and all sorts of other things. So whatever the metric is, we're going to rank it now. So we do this 1, 2, 3, 4, right? So we can do this. We got all 30 of those. What's our next step? Yep, we need to calculate our failure probability. And we learned a new way to do failure probability this year. We used to do like we did n divided by capital N plus 1. Now we have a better way, which is median rank. It's a little bit better. How did it work? We got it. Yeah, minus 0.3 I think it is, and then plus 0.4 on the bottom or something. Did we just pass it?
Yeah.
Right, minus 0.3 and plus 0.4, right? So we'll do I is the rank, so it's 1 minus 0.3. Then over here we're gonna, oh gosh, made it angry. Over here we have to do, and the total number of samples, which is 30 plus 0.4. Okay, so there's our rank. And obviously you multiply that by 100 to turn it into a percent, but there we are. So 97.7% chance of failure there. Again, this is still not getting it right because out of 30 samples, if you go above that, then 30 out of 30 samples failed, 100% of your samples failed. But this tries to correct that because it says like, okay, if you had 1 million samples, odds are that some of these would actually fail above that 578. That's why this isn't giving us 100%. Right? If you just did like 30 out of 30, you'd say 100%. Right? But that's not the right way to go about it. This is a little bit better. Okay. Now what do we do?
Now you can find the y-axis.
Yeah, and our y-axis is this natural log of 1 over the quantity of 1 minus f, right? So it's this terrible thing we have to type out. So natural log of 1 over 1 minus f. So let's write that out. Equals natural log of 1 minus this thing. Again, we're not going to do that as percent. We're going to leave it as a fraction. Okay? And it gives us some weird negative number. That's fine. Now what? I thought it would do that. Next step, that's our y-axis. Now we want ln of our failure parameter. Stress, time, whatever, right? So natural log of this thing. Oh, wait, no, not that. This thing. Oh, I made it angry. Oh, gosh. What have we done? This thing. Okay. Now what do we do? Next step. I'm going to bring this over so it's actually x, y. Right? Now we plot these. What are we looking for now? linear regression, and it's more or less linear. How do we know how well of a linear fit it is? Well, we could do the maths. Where is it? We could punch it into here, right? This is our correlation. This is R. We could go every single point. First off, we could take the average of all those. That gives us X bar. Take the average for Y bars. And then you could plug it in one by one and do it yourselves, or just have Excel do it for you. Really easy to do. This, you're going to do, right-click it, add a trend line, tell it you want a linear one, you want the equation and the R-squared value, and it's not amazing, right? 0.89 is actually not terrific, but it is roughly linear, right? So now that we have that, how would you use this?
Use your slope. That's your margin.
Yeah. So we sort of worked this out right here. We made this expression, which is not a linear expression, look linear by doing that transformation to it. And we got to the point where now we know that y is this. This is our slope. They did, right here's there. Instead of y equals mx plus b, they've done a plus bx, whatever. So the slope is b right there. Right. Or in other words, that's going to be the slope from this line. And then you've got making sure that for your x, you're plotting natural log of your failure parameter, right? So for us, that's easy enough. Our slope is just going to be 6.056. Tell me about the value of 6.056. Is that a high or low value, relatively speaking?
Better low bricks.
It's kind of low, actually. Ceramics that have been like well processed, where there's been like really careful control in a facility, tend to have a much higher modulus. Why? Why do ceramics tend to have a higher modulus?
Less flaws.
What's that?
Less flaws.
Not fewer flaws, but more careful control of the flaws. They're all within a certain type. So you can only do so much to get rid of flaws, but what you can control is try and limit the different types of flaws. And maybe like the last thing you can't get rid of is porosity in your sample, and that's creating a critical flaw, right? As long as that's the flaw, then you should have a tight distribution because you're making it the same way each time. They should all be roughly the same size. If you have lots of variation in your processing, like in your plant, you could have all sorts of things going wrong that give you a much lower modulus and therefore a broader distribution. So when I typed this in, I said, give me an average value between 300 and 600. That's a pretty broad distribution. So our y modulus is appropriately 6. If we were to redo this experiment, which wouldn't take too long if we wanted to, until it only give me values between 5 and 600, I guarantee it would give us a much higher y modulus, right? Which we could do if we were interested, right? Y modulus is a 10 or 20 or not even unheard of if you have a carefully controlled ceramic process, and those are nice to work around because you know then all your stuff fails within a pretty tight range, which makes it easy to apply safety factors. Okay. Speaking of which, how then do we apply safety factors? We've done this, it's great. We took the time to make 30 bars and break them all. How to then, if I tell Jared, okay Jared, if you're making this component, I have to have no more than 100 in a million fail. What do you do? What do you do with that information?
Yeah.
To what? In order to keep 100 in 1 million failing max. That seems awkward. Anyways, you get what I'm saying. What should we do? Lower the stress? Sure. That's always a general rule of thumb. Like lower the stress and more will survive. But how do we be quantitative about it? Or in other words, what stress should I never take this thing above if I never want more than 100 in a million to fail? What's that?
The failure stress?
Yeah, I'm asking you to solve for a failure stress. Yeah?
I mean, when you simply do this, where you look at you wouldn't want your probability that the stress pops out. So,
Yes, right? So basically for failure probability, we're saying it must equal 100 divided by roughly 1 e to the 6th, right? Now realistically, we could try and apply our median rank thing to that and get a slightly better failure probability, but this is a pretty good estimation because we're talking about a million samples, so it's not going to change that number very much. So 100, is that the right number? Let's see, failure, we want 100 out of 1 e to the 6th? Or 1 minus that, let's see. Yeah, we want 100 over 1 e to the 6th. Right? So if we do that, that's going to equal what? Yeah, it's going to be 0.0001. That's F. So that now that we have f, what do we do with it? Natural log of 1 over 1 minus f, right? So this equals natural log of 1 divided by 1 minus this thing. So negative 9.21. Where's negative 9.21 on this plot? Not. It's not on there, right? So it's going to be way over, right? So we could extend this out. It's not a big deal. We could say, let's just draw this on here just so that we can see it. Let's have it go to negative 10, right? So somewhere clear down here-ish, we want to know where that line intersects it. Clearly it's going to be way below the 5.6 that this currently goes to, right? So you could change that just so we can see it. Have it go down to like 2, for example, right? It's going to clearly probably cross it around maybe 5-ish. So let's give ourselves a little more room, okay? So now we have that. What do we do next?
Are you just guessing what it's going to cost? Or you?
Well, you could guess. You can be accurate about it, though. I mean, this is spitball. It's saying negative 9.2. It looks like it's going to cross that at about, after that line, yeah, somewhere around 4.5-ish. But how do we do quantitative?
Plug negative 9.
Yeah, just plug. We have a y equals mx b equation, right? Y equals mx plus b. We know what that is. Let's actually type it out. Equals, what is it? 6.05 x minus 37.23, right? So we've got our y equals mx plus b. So just plug in for y and solve for x. So x equals, somebody solve for x. I guess we could do it together. 4.62. Beautiful. 63. So fast. Okay, so we've got x. Now what? Are we done? Can we only take it up to 4.63 megapascals or whatever? No, we're missing a step because this x equals, remember, x equals natural log of your failure parameter. So now we need to solve for the failure parameter, we do what? Equals exponentiate of this thing. Oh, now I've done it. Okay, there we are. 102 megapascals or 102 hours or minutes or whatever that was that we were talking about. And then if you take it up to that stress and you say, all right, in real life, if you never subject this thing over this 102, then you should never have more than 100 in a million fail. Right? So you've seen this before. So I'm just re-emphasizing it now because in ceramics it's a big deal. Because they're so prone to brittle fracture, you get no warning when they fail. It's oftentimes sensible to design it such that you just know that never going to have a greater failure than X amount. Okay? Any questions on Weibull? Now, we covered one more thing in 2010 that I'm not going to go into detail now here, but it's extrapolating this to larger components, right? One of the big advantages of this is that if I wanted to design freeway overpasses, it'd be nice to make small cement samples in the lab that I can test, instead of making 30 freeway overpass pillars and testing those. It's not super practical. What's the catch? What do I have to do? What do I have to know? Right? So this tells me 102. That's what I get. If that's the value I got for my cement for my overpass, right? Or whatever. Is that the same value I can use for the freeway overpass? We have a vote yes. It's not the right answer, but what's your rationale?
Well, it's a stress. So, I guess floss size should be different, right? But
that's it, and that's exactly it. Why should floss size be different for the thing that you make in the lab versus the same material, the same process, but on a much larger scale? Yeah, Barrett?
Log distribution is going to be different throughout the larger material. And so you might have larger points that come out speaking in the center of it, or
yeah,
depends on the material.
So you don't want two different types of mechanisms. Otherwise, you can't apply Weibull analysis to it. You want it to be the exact same material, made the exact same way, just more of it. Because then I think Jared mentioned that just the probability of having that flaw just gets larger and larger. If there's something about your process as you go from a small scale to a large scale that's just inherently giving you a different type of flaw, like maybe, I don't know, nit lines from where it's pouring from a larger thing, like that, it's a different mechanism of failure. So your Weibull analysis will not be applicable. right? But if you make it the exact same way, cast it the exact same way, you're just doing more of it, then just odds are, the more volume, the better your odds of having that flaw. It statistically scales with it. So what do we need to fix it? We need to know the effective area, right? The effective area over which your sample is experiencing its maximum stress is not going to be the same for something in the lab as for a giant freeway overpass. So you need to know that effective area. And if you know that, then you can scale this. And we do that in 2010. Okay? Any other questions on this? Should we move on? Okay, we'll keep going. Save this.
So is that slow? It's just useful when you compare it to other things? Or does it have that?
It's useful, like, how about this? Let's do another example of this, where this time, this goes from 300 to 600, right? So what's our average value here, right? Let me do it right here. Equals average. The average is 442. So we could make another setup. We could do this over here. We could say, give me the random between, let's do 300 and 400. So clearly our average is going to be lower, but is our distribution tighter? Yeah. So the question might be, and this is something I'll regularly ask students, I'll give you this, right? And then we post it as the values. And get rid of that. Well, I'll just leave it for now. Right, so it's these values we care about. So which one's better to use? You've got two different processes, or maybe you're talking about, maybe you're not even making these ceramics. Maybe you guys are just engineers and you're going to use these things. One company says our average strength is 442, and the other one says our average strength is 353. Which one should you use? And you, at first blush, most engineers would say, if I don't want this thing to fail, let's use this stuff, right? You all agree? And it seems like a better choice. Tell me why this is maybe not a better choice.
Designing for failure.
If you're doing probabilistic design, when you're designing for failure, why could this material on the right be a better choice?
Having probability of failure due to that.
Yeah, but basically it's like this is a tighter distribution than this one, which means if you need very, very few to fail, you're actually going to find that this one's better. Let's prove it, right? That seems really counterintuitive. Let's show it. So we do the exact same step as before. So we do our natural log of our failure. First, let's determine failure, right? So we have to rank these things. So let me sort those and hope that the world doesn't end. I just won't. I won't extend it. So go smallest to largest. We do not. Okay, right? Now we've got that. This thing hasn't changed, right? So now we have to do failure. We decided that's equal to, oh gosh, I'm gonna move this down. All right, let me fix this real quick. That's really unfortunate. All right, so I have to fix this. So this thing, average. I think it's because I'm forgetting a bracket. Okay, so we've got that. Okay, it's still basically the same, right? Now when we calculate F, we can do... Yeah, every time you calculate it, the formula redoes it. Oh, I need to paste that. Ah, all right, sorry. I think this is worth our time, so I'm gonna go. I'm gonna carry on through this. All right, so we've got those now. This thing technically should be off of the next column over, but whatever. It's gonna be close to the same, right?
Value should be the same as previous.
Yeah, let's just drag it over. There we go. So these things are going to keep changing. Just ignore those. This is still lower average than before by 100 megapascals, right? So it still looks like, hey, that's a crappy material. Here I'm going to show you that it's probably better for the scenario that we just calculated, maybe, right? So how do we do this? We need to calculate F. So we're going to do F equals this thing plus 0.3, or is it minus?
It's going to be the same as the other one.
Oh, it's the same. Good call. Let's just copy it. So here's our F. It is the exact same, right? Paste that as a value. And then we have to do our natural log of whatever stuff. So here's this one. We need to grab this column. Right? And then, so that's our natural log of failure. Then we need natural log of 1, blah, 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 minus f. Right? Whatever that is. Which should be just the same as well. So you can, yeah, this should be the same as well. So I'll just copy and paste that as values. So now we are there. We have x, we have y. So I should be able to plot these, right? And add those to our plot. Let's do it. Let's come here. Let's select data. Let's add a new one. New. We'll call this our x values. Go here. Add our y values. Ta-da. Whoa. Something's super wrong.
Yeah.
Oh, I didn't rank these. Son of a gun. All right, let me fix that. Why is that so long? What possible reason do they have for such a long box? All right, so this all needs to be ranked, right? So let's sort that. Smallest to largest, and let's not extend it. Does that fix everything? Yeah. Okay, now we add a line to this thing. Make it linear, blah, blah, blah. So look at the Weibull modulus on that, 14, right? Totally reasonable to get that for materials. Now tell me which one's better, and tell me why. Let me make this bigger.
Well, our squared value is also way better.
R squared value is also, it's more linear. But why is this a better material for this application?
You can predict it a lot better.
Well, to have 1 in 1 million fail, that corresponded to a failure value of 0.0001, which means its natural log of 1 over minus f was negative 9.21. Yeah, Chris?
So would this be the case, just that you figure out how to isolate one flaw size so that it's very faithful?
Yep.
This flaw's going to fail, not like a crazy distribution of flaws.
Yeah. Even though in this sample range, your average value was higher, this one's clearly lower, its average value. Because this is a tighter controlled flaw population, it's a tighter distribution, it's actually better for this application. How we solve for that is we know that the failure criteria, natural log of 1 over 1 minus f, is this negative 9.21. So that's clear over here. So where are those two lines going to intersect? Right? Can you extrapolate? You can extrapolate these lines, right?
Yeah, they already intersect.
They're already intersecting, right? But I just want to show
You
this.
can go back a few periods.
Can you extrapolate?
Forecast.
Forecast back. How many periods? What's a period?
Like 10.
I don't know what that even means. Let's try this.
There's
Ah,
the
beautiful. Okay, and over here. Go back. So what is it, period? Do we know?
It automatically shows one period, so it'll move forward the same amount of x as you already, like it'll take us the line and add it to it if you look forward one period.
Gotcha. Perfect. So we intend to that. Way more. So negative 9 is around here, right? So at that point, this thing has an x value here which corresponded to a lower stress. Lower x, lower stress, like 100 MPa. This one can actually withstand 5.27, which is how many megapascals we take e to that. Take e to 5.27.
That's 194.
So this thing can, it's twice as good basically, right? It's super counterintuitive, right? At first blush, you're like, hey, this thing's got average strength of 450 versus 350. This is a way better material, but because the distribution is broad in this material, it's actually undesirable to use for this scenario. Now, if your failure criteria was something higher, you can withstand 50% of them failing. Yeah, then the other one's better. But at some point, when your failure criteria, when these cross, and your failure criteria is right around here, it stops being beneficial, right? It's a good example. I haven't done before. So if you came to class today, pay attention to that. At what failure criteria would be better for two different distributions to switch over? Hint, 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 hint. Okay? Okay, let's keep going. Any questions on anything we talked about? Probabilistic versus whatever design? Thomas?
Would companies release that data to you?
Weibull modulus?
Yeah.
You can request it. Yeah, sometimes that's, I don't know if that's regularly on spec sheets. If it's from a ceramics company, it's more likely to have it than like a metals, because our friends in metals sometimes forget about Weibull and probabilistic design, right? And sometimes it's not relevant because it's gonna be plastic, right? They're not subject to brittle failure where Weibull really shines, because many Weibull materials fit this nice Gaussian distribution. Right? When things can deform heavily, you don't always get this nice Gaussian curve, and so sometimes they don't do it. But a ceramics company will often report it, and if not, you could say, hey, I want the Weibull date on this because I'm doing probabilistic design. I need to know the distribution of failure to 30 plus samples. Right? Okay, toughening. So this is the last thing we're going to cover in this class. We've got half of class today and a full class tomorrow on it. Toughening in ceramics is critical for the exact reason we've been describing, that ceramics tend to fail under brittle failure, right? They don't just like slowly give you lots of warning that they're going to go, they just fail brittly, right? And therefore it's catastrophic and undesirable. That said, when you have a ceramic fail, it always involves two processes. You have to have a crack initiate, right? Something that starts the crack, and then that crack has to propagate. And if you impede either of those two processes, then you've toughened your ceramic, right? That's in a nutshell what this chapter is going to be about. If you can impede crack initiation or impede crack propagation, you've toughened your ceramic. So one of the papers I'm having you read for this homework is Lang's paper, Fred Lang. He passed away close to 10 years ago. Amazing ceramic guy. His whole shtick was processing of ceramics. How do we introduce a scientific method? Being very quantitative about how we talk about processing of ceramics, and particularly the flaws that processing creates. And the paper that I'm having you guys read for the homework this week is terrific. It's a really good overview of here's the right way to process ceramics to control flaw populations. So I hope that you've already started reading that. It's really good. Then the next one is, all right, if a crack is going to propagate, how do you slow it down? What things can slow it down and impede it? And that will increase your fracture toughness. So when you stress a ceramic or any other material, you're actually storing energy into it. That should make sense, right? Intuitively, if you stretch something, while it's stressed, you're storing energy into it. So some of that stress is what we call elastic, right? Meaning what?
It's going to subtract.
Yeah, it's going to rebound, right, back to some shape. It's an elastic, meaning it's a reversible change. It's going to go back on its own. And some of it is plastic, right? So in your diagram, when we plot the stress versus strain for these things, right, we plot stress versus strain. And you've all seen these from 2010, that different materials have different things. Like a ceramic might look like this before it fails, whereas a metal might do something like this, right? Polymers might do something like that. The area under this curve is the energy, right? That's the energy that's getting involved in this deformation process, right? In the case of a metal, you've got your region right here, which is plastic, right? When it's still linear, elastic, I said that wrong. This linear region tends to be the elastic one, meaning you can unload it and go right back down to zero. But once it starts to become nonlinear, generally speaking, that's when plastic deformation occurs. But there is certainly non-linear elastic material, right? Where it does this, but it's going to actually recover. Right? Goes like concrete is an example of a non-linear elastic material. How does this give us units of energy? This is stress versus strain. The area under the curve is normally, right? So what are the units of strain, Christoph? What's that? It should have no units. Strain is just percent, right? So it has no units.
Notice like inches over inches.
Yeah, that's why those cancel out. They'll often write it at inches over inches or meters over meters. And this has units of something stress, like MPa, right? So it's MPa. A Pascal is what? Newton per meter squared, or a joule per meter cubed. So that's where your energy is coming from. And that makes sense, because if you test a larger object as opposed to a smaller object, you're going to store more energy in the larger one, right? So this is like, it's proportional. You have to take into account the volume of your object, right? But this is the energy that's going into it, right? So a lot of the processes that make your material tougher have to do with this energy. They absorb more energy during the crack propagation or initiation process, right? So as the crack grows and you're deforming this thing more and more, if you can absorb more area under this curve, then there's more energy getting put into there, so you've made it tougher for it to propagate, therefore it's a tougher material. Yeah.
So when we're seeing like the curve start to go down again, is that saying that it's losing energy?
No.
Or
No.
is
When it
still
goes
gaining
down,
energy?
first off, that's just a function of the cross-sectional area changing. Like a metal can start to neck, right? Meaning that you start out with some cross-sectional area, maybe a centimeter cubed, but because that starts to draw down, you guys have all seen this, so I need to pull the image. You've seen it next down. Just that because the cross-sectional area is going down, the engineering stress goes down, but the true stress is actually increasing. But does this mean it's storing less energy? No. Like if this line keeps going that way, your area under the curve is getting bigger and bigger. So it's still getting better and bigger. Okay. So what are your options to avoid fracture? What do you guys think? Turn to a neighbor and what are your options to avoid fracture?
Better plastic over your lines. Don't pass. Don't go over your plastic.
Okay, what are you guys thinking? Ideas for preventing fracture? What do you think, Jake?
The amount of time between the stress, so like rather than subjecting to large stress over like a really short time, make the amount of time out. That way it's not all complicated in one.
Yeah, what do they call that in physics? It's not the impulse, is it?
Yeah.
Impulse? Right? And this is why they put like cones in front of pillars on freeways. If a car hits a freeway overpass, cement, it's going to arrest its motion very quickly. So its impulse is is it a high impulse or low impulse? That's high impulse. I mean, the change in momentum is over time is very rapid. That kills people, right? But if you hit a bunch of barrels and it slows down your change from going 6 miles an hour to 0, in both cases you go from 6 miles an hour to 0, but it spreads out the time over which that happens, which is beneficial. So yeah, maybe you could think of something like that if the crack's going to grow, what if you could just make it grow slower? Is kind of maybe one way to think of it, or something like that. Yeah, that's a great idea. Other thoughts? Yeah, Barrett?
You could add other materials to your ceramic that would take some of that stress and
Like,
Yeah, exactly. Like rebar. Yeah, so they take that with cement and they'll put rebar through it. And then when you load it, what is those other materials actually doing? They're carrying the load. You want them to carry the majority of the load, right? So that if the material's under load, your matrix, which is maybe brittle, doesn't have to see such a high load since a lot of that is being carried by the rebar, which is not brittle, right? So making composites, particularly fiber reinforced composites, which we'll talk about this chapter, are a great way to go, right? Generally speaking, I was using a scribe on my screen. That would have been real sad. That would have been real, real sad. I'll set this over there so I don't grab that again. Fewer stress concentrators. So controlling your processing to get fewer stress concentrators. Which, remember, a stress concentrator is basically anything. Another phase could be at a grain boundary, certainly a pore, inclusions, all that stuff can cause the stress concentrators. And then the other one is this general term of store more energy during propagation. But I like the thoughts that you guys had as well. I should add on some more of these in the future. So what are our toughening mechanisms that the book at least talks about? One of them is the one that Barrett and Jared were saying, modulus transfer. Modulus transfer. So you embed something with high modulus, like a fiber, into a low modulus matrix. So if you've got cement, which has some modulus, but you put something with a higher modulus into cement, when you stress that, the high modulus material will do what? Like, I guess the question I'm getting at is, why does it have to be high modulus? Instead of thinking of energy, think about it in terms of deformation. Why do we want a high modulus fiber as opposed to a low modulus fiber? Why would the other way around not work? Yeah, Barrett?
The high modulus fiber won't conform as much as the low modulus fiber.
Correct. So in terms of this diagram, this might be the high modulus material, and this might be the low modulus one, right? The slope here is higher than here. So why does that help us, Chris?
Because they're both being performing the exact same amount, but the high modulus will be able to store more energy in it, whereas
Yep.
the low modulus is much less energy.
Yep.
That same amount of deformation.
Yep. Like if this is the whole thing's being stretched to there, some strain. This one is going to reach this limit before that. Or sorry, this one is at a higher stress than that one, right? It's going to be carrying more of the load. If you pull on something, imagine you got your rebar in there. If it's a high modulus material, that is not going to be able to strain as much as the. So another way to think of elastic modulus is stiffness, right? This is a stiffer material than this, right? So if you pull on something, the stiff material, it's not giving anymore, right? Whereas the not stiff material is still willing to give. Since it's still willing to give, it's not carrying the load. The material that's stiff can't go anymore, so now it's carrying the load. It's transferred the load, so it's modulus transfer, right? Does this make sense? Why it wouldn't work the other way? If you had a high modulus matrix and a low modulus material inside of the yeah, fair?
So if your high modulus material fails, it breaks, does it give all of that energy onto your matrix?
Great question. So the question is this, like imagine that we had some sort of fiber in a material, right? So here's our matrix, and then inside that matrix we embedded some sort of fibers, right? What happens, he's asking, when this thing breaks, right? You go above its strength, right? So for a given stress, this thing can only hold that much stress. When it gets to that point, this will now break, right? What's going to happen? So this thing splits, what happens?
Stress just transferred to the lower.
The stress transfers to the lower modulus material, right? Now there's something else that can happen sort of in between there, which is fiber pullout. And we're going to talk about that in a moment. Basically, while you're pulling on this, now even once this splits, these things, if you're pulling on it, they're now going to get pulled out, right? As you get fiber pullout, this can actually be a toughening mechanism. It is a toughening mechanism. Why? Why should that toughen a material?
It's basically like you're friction.
Yeah, you get friction, right? So there's a bond between your ceramic fiber and your ceramic matrix, or your whatever these things are made out of. There's a bond at this interface. If you start pulling that, as this thing drags out, this fiber pullout occurs, it's a lot of friction force. That's going to make it, it's going to store more energy, right, for sure. Basically, yeah. It's going to store more energy in the deformation process. We said anything that increases energy storage during deformation, during crack propagation, is going to toughen it. So that is a really good toughening mechanism. Even though you say, hey, I know this thing's going to break, right? But I don't care because as it pulls out, it's going to store lots more energy. You're going to make it a tougher material, right? So it is absolutely a toughening mechanism.
But that's going to be a material that you can't reuse it, right? It's going to serve one purpose as...
It's not reversible. Yeah, you can't heal this unless your material, you could put it back together, do some sort of heat treatment, and cause these basically to go back in and then rebond. Maybe you could melt your matrix like a thermoplastic. You know, I'm sure these things exist, but generally speaking, these are relatively brittle-ish materials. They're one-time usage. So it's going to extend its lifetime, but it's not like going to be rechargeable per se. I think for most applications. I could be totally wrong. There could be instances where it is, you can heal it. I just don't know everyone. Right? So there's lots of examples of this. We do it all the time. Fiberglass. Fiberglass is epoxy. What's the modulus of epoxy? Really low. Right? On the order of a gigapascal. Really low. As opposed to ceramics are like several hundred gigapascals, right? I think epoxy probably even less. It's probably a sub 1 gigapascal, right? And then fiberglass, you have glass fibers running through it. And if you've ever seen these, like an old boat or something made of fiberglass, they're usually just all over the place, right? Kind of looks like a spider's web, but they're embedded in that epoxy. So if you were to break this thing, let's say your boat hits a rock and it starts to crack and start to break and tear apart, you're going to have to, the load's going to transfer to those fiberglass, the glass fibers, first off, and then as those get pulled out of the epoxy, it's going to give it a toughening, right? If you ever tried to break fiberglass, it's actually hard to break, right? Those things do sort of rip out, and it's a relatively tough composite material, right? But there's metals where you take aluminum metal and put silicon carbide in it, or steel silicon carbide. Silicon carbide is a really, really strong, high modulus strength material. It's very brittle on its own, but if now you've embedded that into a metal, you can really toughen it. Put carbon fiber into epoxies, you get the same sort of effect. So there's lots and lots of examples of this that we use all the time. But they're not all equal. Not all composites are the same. Like even if you make different, like you say, oh, well, all fiberglass is not the same. Even those are different. How can different fiberglasses have different properties? What are we changing? Yeah, fair?
Length and thickness of the fibers.
Yeah. So like the diameter and the length of these things. Like what if this diameter, what if it's really, really small, right? What if the fibers, instead of looking like these long, continuous fibers, what if your fiber looks like this? Oh, we've lost it. We've lost it, gang. Yeah, if it won't pull out, then you don't get the whole benefit of fiber pullout giving you the toughening mechanism, right? So that's not going to help you very much, right? So, in fact, there's a value, I've got my notes somewhere here, where you want your ratio to be 8:1, the aspect ratio. What's the aspect ratio? We've heard that term before.
Yeah, the length of the fiber versus the original fiber.
Yeah, the long side divided by the short side, that's your aspect ratio. And you want that to be 8, roughly. Right? Something short like that, even if it does break in the middle, it's not going to pull out very far. And odds are it may not even break in the middle. It might break in the crack might go around it, right? And then you get crack deflection, which is also good, but probably not as much of a benefit as fiber pullout. Right? Crack deflection is good though. Yeah.
I'm curious, does fiber pullout like make a really big difference to the strength of the material, or is it just kind of like a little bit?
That's a big difference. Yeah, that gives you a really high increase in fracture toughness. I think I have some values later on in this chapter where we'll talk about how much of an improvement you see in different materials with these different mechanisms. So we'll see some of those. So diameter, length, all that. The strength of the fibers. If you put in a really high modulus material that's just not very strong, it's really stiff, it's just not very strong, then it's going to break at a lower stress, right? So it's going to absorb less energy. You want to go higher up in that stress versus strain curve. The bond, what about this bond? What if that bond is so strong between the fiber and the matrix? Like a really, really strong bond. Is that good or bad? Why is it bad? Yeah, like a crack that comes through this thing might do the following. It might just split all the way through it, and without being able to pull the fibers out, you don't get that extra friction, that drag force that's storing energy, then you don't get the benefit, right? So it's this interesting game where you don't want these things too loosely bonded, because then when it pulls out really easily, and you don't store a lot of energy. But you can't have it too strong where it won't pull out at all. So there's like this there's this optimal range for bond strength there to get your maximum amount of toughening, right? Okay, what's the main points? And then the last one is volume fraction. Fiberglass is not fiberglass is fiberglass because you can have different volume fractions, right? Even if it's all like epoxy and glass, the same exact materials, the ratio could be different, right? You could have 60% fiber versus like 30%. And then what's the last thing is orientation. The way that you orient these fibers. If you take a fiberglass boat where there's like a spider web and they're randomly oriented, that's going to have one set of properties. If you take another boat where it's like layers like this followed by layers like that, and it sort of lays them up like that, that's going to have different properties. Not that one's better than the other. You're going to have higher values in the oriented one, but it's only higher in certain directions. The average value for strength is going to be better for the random one, right? So depending on your application, if you know that it's going to be loaded in just one direction, like you want a beam and that beam just needs to be strengthened, it's way better for you to line your fibers up oriented to the direction where it's going to be loaded, right? So you maximize the largest amount of modulus transfer to the fibers, right? But if you need it to just be like a general all-purpose, you don't know where stress is coming from, like a boat hole that could hit a rock anywhere, then it's much better to have a random orientation, right? So because of that, in the field of composites, they'll take these fibers. How do we make fibers? Ceramic fibers, this is aluminum fibers. How do you make aluminum? How are you going to draw aluminum though? Drawing involves a really plastic process, so you can maybe like chock it full of binder and try and draw it. I don't think that's how they do it. I think most fibers are almost always pyrolyzed. I could be wrong about that. Aluminum, I don't know. I think you start with some sort of polymer precursor that you can draw out though, then you convert it, you pyrolyze it over. I could be wrong about that. I think that's right though, right? You start with this though, and you're going to embed it into some sort of epoxy. And the way that you do it, you've got lots of options, right? It could be no, this is common. Like you see skis. Have you ever like saw into a pair of skis? You break a pair and you see it. You'll see lots of different layers, which is doing exactly what I described before. They might be 90 degrees from one another. They might be 45. They might have some other random angles, but it's trying to maximize in-plane stiffness by doing that, by laying out the different orientations, right? When you do lots and lots of different orientations, you can get pseudo-isotropic properties, meaning it kind of looks like it doesn't depend on the direction. Of course, we call it pseudo-isotropic because this is still happening in 2 dimensions, right? In a plane. If you're pulling this out of its plane, right? If I were to like attach suction cup to these and pull on it, that's going to have wildly different properties than if I pull in the plane anyway, right? Because the fibers aren't able to load the transfer, right? You don't get the modulus transfer benefit, so it's not tough. Yeah. Which is why skis and snowboards, you ever see it, they don't tend to break right in half. They tend to like peel. Something breaks a layer and then it starts to peel off, right? You've ever seen skis or snowboards that hit a tree? It creates delaminations, not fractures, generally speaking. Right? We already talked about, is there a length that's too short, too weak? Because of, so we mentioned this earlier. We said, if you're going to put a material running through it, like rebar running through concrete, it needs to be a higher modulus to get the modulus transfer. So is steel rebar, is that higher modulus than concrete? Definitely not. So what's wrong with this scenario? Why do we put rebar in it then?
Did you like stretch it first? And
Yeah,
release it?
they do it because they can pre-stress it, right? You can take these things, you could have a mold basically where you're going to cast the cement into, and before you cast the cement into it, you fill in these fibers, right? You can apply a load to them, so now they're pre-stretched, right? Then you cast your cement, right? You let it set up, and then when it's set up, you then release the load on those steel fibers, and they want to relax, right? Because they're in their elastic region up here, right? They want to do, we've loaded them up to some level, they want to go back down, so they're going to shrink, right? And the amount of they're going to shrink will do what to the concrete, which is now, yeah, it's plastic, or it's a material that doesn't deform plastically. It can be strained a little bit. So interestingly, as the steel goes down to rebound, that causes a subsequent climbing here. They're going to meet somewhere in the middle, right? So it puts the concrete under compression and the steel under tension. What do we know about ceramics and compression?
They love it.
They love it. They love some compression, right? So this is it's a pretty clever thing they do, right? They do that because it puts the whole thing under compression. Therefore, the ceramic before it can, since it's going to be the thing that breaks probably, it's less likely to break because you pre-stressed it, right? You put it compressed straight all the way through, which is really nice, right? How could you do this with temperature? How could you do this with thermal expansion to get the exact same result? So turn to a neighbor and discuss this. This will be the last thing we cover. We'll pick up here next time. So discuss with a neighbor. How would you go about the same result with temperature? Josh, we didn't get them. I'm sorry, man. Let's do them on next class. And let's hunt down the blowtorch ahead of time. Find it. See it? Let's find that. Yeah. Well, she did the demo on Friday. Maybe she hasn't put it on Marcy. Maybe she's got it. But let's find it and do that demo on next class. Aren't they cool? That's a sweet one. Like I've emailed a couple people asking for recipes to do those big glops like that because they work so well. No one's gotten back to me, so I want to figure that out. Like a good glass recipe or a good stock glass material to start with. I haven't found one that works as well as theirs. Okay, comments? What do you guys think? How would you do this taking advantage of thermal expansion? What would be the steps you would do to achieve the same result?
Heat up the rebar.
Okay, so the rebar is preheated. So it did what? When you heat it, it's going to expand. Is it expanding more or less than the concrete?
More.
So do you want to heat it before you had the concrete or after or what? Could. What if you, let's try this scenario. If you did cast it just as is, right? Then you heat it up before the concrete sets up. Okay, yeah. So now it's in a stress-free state. It's just higher temperature. What will happen when you cool it down? Say again. Heard multiple people say things. Brian, you have something?
Might help to reach radially and regularly.
That's one possibility. Yeah, actually, that will happen. That will happen. Because the metal's going to shrink more than the concrete. So the concrete, the holes that the concrete has in it is going to shrink, but the metal is going to shrink more so it's going to debond a little bit. That's actually right. It will a little bit. Which one's going to expand more, shrink more? How do you know that? How come? Metal bonding, which is weaker bonding. Lower melting point comes with lower bonding and therefore lower thermal expansion. So yeah, if you did this with metal, I've actually never thought about the point that Ryan brought up, and I wonder if that's a deal breaker. It might debond from it, and then you're out of luck. If it doesn't debond, this would work. Because as you cool it down, the metal's going to shrink more than the ceramic. Therefore, as it's shrinking more, it's going to put the ceramic under compression. That's a really interesting point, though. Yeah, Jake?
Can you let it cure at like a slightly higher temperature than what we would be at under like normal circumstances? So, let's say you're using concrete, you let it cure at like 120 degrees Fahrenheit. So, and then once you subject it to normal temperatures, it'll just compress a little bit to begin with, and then just very compress the space.
I think that's exactly what we're describing. Yeah, I think that's exactly what we're going after here. Okay, we'll pick up here next time.